Hello, my name is Matthias von Bruch and I am going to give you an introduction to the new class of moment tensor potentials, or MTPs. In this introduction, I will be talking about classical potentials and their limitations, in particular EAMs, the gap between EAMs and density functional theory, or DFT, and then we're going to dive a bit deeper into the requirements of interatomic potentials, meaning what is necessary for them to accurately describe interatomic interaction in a computationally efficient way. Of course, all these requirements are met by MTPs. But they are not just great and accurate interatomic potentials, they actually have a few other interesting properties which can also help optimize a scientist's entire workflow with respect to alternative potential formulations. One of these features that will be covered is learning on the fly. I will then show you how MTPs are implemented, meaning which software you'll need to use them. You will then know what you need to do in order to use MTPs, so I'll also give you a few suggestions on what you can do with them, meaning that we'll discuss their capabilities and potential use cases. In the end, I'll summarize everything to give you a concise overview over everything we talked about and make sure you don't miss any crucial points. So let's get started. Classical potentials, such as embedded atom method or EAM potentials, are widely used to perform molecular dynamics or MD simulations. A number of different formulations exist, which vary in their amount of fitting parameters, and therefore in the type of system that they can describe. Simple empirical potentials, such as the Lennard-Jones potential, for which the formula is shown here, could theoretically be used to run MD simulations, and their simple analytical form could make for very fast evaluations of energies and forces, and thus for very fast simulations in general. However, with only two free parameters that could be used to fit the potential to a given system, one cannot expect to obtain accurate results and therefore quantitatively useful information for any system. Let's see why using a Lennard-Jones potential would be problematic. Here comes our potential. Let's vary its free parameters so you can see what kinds of different shapes this potential can assume. For each type of atom, this shape will need to be adjusted. Okay, this looks reasonable, doesn't it? You can vary the location of the minimum of the potential energy, which will adjust the atomic spacing of the simulated material. You can also adjust the depth of the minimum, which is effectively controlling the binding energy of two adjacent atoms. But let's look at this animation in a somewhat different way. Here, you see the exact same variation of the potential, but instead of a moving line, you just see moving axis ticks. So the general shape of the potential never changes. It always looks the same, only that we can stretch it in two different directions. When this is the only thing we can affect, you may already have guessed that this is of limited use to quantitatively analyze atomic interactions. In fact, any material simulated by this potential is collectively called Lennard-Jones substance, meaning that any change you make will not qualitatively alter the behavior of the material. This point is intuitively understandable and valid for any potential parameterization. The higher the desired accuracy of the potential, the more complex the required model, the more free fitting parameters must be available, and the more complex the evaluation of forces and energy during runtime. It is the usual compromise between speed and accuracy that anyone working in the field is so painfully aware of. The question what kind of potential is best for a given simulation is by no means a trivial one, as the choice not only depends on the elements present in the system, but also on the physical phenomenon under investigation. The simulation of vacancy formation energy in a metal, in which all atoms can be assumed to be somewhat close to thermodynamic equilibrium, may indicate the use of an EAM potential, whereas the simulation of the development of radiation damage may call for the use of screened Coulomb potentials, which may be less accurate in some areas, but describe the force between atoms in very close proximity well. Many more types of interatomic potentials are available, some of which are listed here. Generally, interatomic potentials can be classified according to the amount of atoms that are considered simultaneously during force and energy evaluation. In a single-body potential, no interactions of atoms are considered at all, which makes such a potential quite useless, since it can only describe external potentials such as an electrical field. The Lennard-Jones potential would be a two-body potential, since the distance between two atoms is evaluated. Such potentials are, however, by design not capable of describing certain materials' properties, such as all three elastic constants of cubic metallic systems simultaneously. If you wanted to evaluate the forces between an atom and multiple others, you would have to do that consecutively. First, you evaluate the force between the blue and the yellow atom, and then between the blue and the red atom. This is fundamentally different from how a three-body potential works, which would consider the positions of all three atoms at a time. This allows for a more fine-grained control of atomic interactions. Many-body potentials, which include direct interactions of an arbitrary amount of particles, also exist. Let's have a more detailed look at embedded atom method potentials, because they are very popular to describe metallic systems, because they assume that a kind of electron gas is present and that directed, covalent bonds do not play a role. This type of potential is a member of the class of many-body potentials. It is ignorant of any kind of directions and therefore cannot describe energy gradients with respect to angles, as would be required to reflect the notion of atomic orbitals necessary for directed bonds. This parameterization involves three functions, and one for nickel is shown here. The first one, drawn in blue in the top figure, is called the pair potential. It gives an energy as a function of interatomic distance between two atoms. For every combination of atoms in a simulation, a separate pair potential exists. The second one, drawn in green, is called the electron density function. It describes the contribution an atom makes to the electron density surrounding it. In practical cases, this function often does not reflect the actual electron density, but is seen purely as a fitting parameter and can even become negative. Thirdly, there is the embedding function, shown in the bottom figure. Its job is to describe the potential energy of an atom due to the electron density at its current position. The many-body character of EAMs is fully encapsulated in the interplay of the electron density function and the embedding function. All atoms in the neighborhood contribute to the electron density, so the embedding energy depends on the positions of all atoms. Now we know how EAMs work. What we need to know is how accurate they can be and how much is missing to one of the most accurate models available to us today. I'm referring to density functional theory, or DFT. EAM potentials are accurate enough to allow qualitative investigation of materials properties of many systems. They are also very efficient, allowing MD runs with several hundreds of thousands of atoms over several nanoseconds. This may not sound like much, but is actually sufficient to investigate a wide range of materials properties. However, quantitative analyses of materials properties are seldomly reliable, and potentials are often fit to accurately describe certain scenarios, like surfaces, but are inaccurate in others. So even for one given system, one must often choose from a pool of potentials the one that is best suited to describe the phenomenon of interest. Within this inherent inaccuracy, though, it is possible to simulate a wide variety of things, from bulk properties to surfaces, grain boundaries, defects such as dislocations, and more. To achieve higher accuracy than provided by EAMs, one usually had to resort to much more computationally expensive methods such as DFT, which attempts to accurately describe the quantum mechanics at play during atomic movement. This involves applying the Born-Oppenheimer approximation to generate the wave function of at least the outer electrons of each atom, increasing the number of particles that need consideration drastically and requiring a much more involved theoretical treatment. As a result, the number of atoms that can be used in a simulation is drastically reduced, making computations involving more than a few tens of atoms infeasible. As one can see, there exists an enormous gap of accuracy and efficiency between the two approaches, leaving scientists with a crude choice between complex systems at low accuracy and tiny ones with very high accuracy. Little could be done to bridge this gap. In this work, I present a new approach. Moment tensor potentials, a new class of classical interatomic potentials with an arbitrary amount of fitting parameters and machine learning capabilities, are already relied upon to provide near DFT accuracy at a computational cost of about 30 to 50 times that of EAMs. An investigation of the accuracy and stability of these potentials can be found in my master's thesis titled Accelerating ab initio thermodynamics using machine learning potentials. To understand what makes MTPs such powerful tools for simulations, we must first understand the general requirements of interatomic potentials. The first requirement of interatomic potentials is for smoothness of the energy surface with respect to atoms leaving and entering the cutoff radius. So what does that mean? For efficiency reasons, not all interactions of atoms in the simulation are considered when evaluating the energy of a single atom, since that would mean that the computational cost for energy evaluation for a single atom increased with the system size, which would quickly outgrow our computational resources. Also, in most systems, this approximation is a very good one, since interactions usually become negligible between atoms with a sufficient distance. Therefore, only atoms that are closer to each other than a certain cutoff radius, which is typically about 5 angstroms, are considered. The requirement of smoothness essentially means that the interaction between atoms as described by the potential must drop to zero before the atoms leave the cutoff radius. Otherwise, since forces are proportional to the gradient of the potential energy surface, an artificial, extremely large force would be introduced whenever atoms reach the cutoff radius, leading to large errors in any atomistic simulation in which sufficient atomic movement is present. By the choice of appropriate radial basis functions, this requirement is easily fulfilled by EAMs, since both the pair potential and the electron density function eventually drop to zero. MTPs also fulfill this requirement by employing appropriate basis functions, but they cannot easily be plotted due to their more complex form. The second requirement is for invariance with respect to rotation, reflection, and translation. Intuitively understandable, the energy of an atomic configuration should not depend on the angle or the distance from where it is observed, but only on local environments. That means that within a chosen coordinate system, the energy of an atomic configuration must not change if it is being moved as a whole, rotated, or reflected, as shown in this figure. Depending on the complexity of the mathematical model chosen to describe atomic environments, this may be challenging to achieve or at least to prove. In the case of EAMs, it is straightforward, since once again, all energies effectively only depend on atomic distances, which are invariant with respect to the aforementioned operations. In the case of MTPs, this requirement is also fulfilled, but the proof is rather complex. The third requirement is for a complete description of local environments. To describe the energy of an atomic configuration accurately, one must first describe the configuration itself accurately. This means that any local environment of atoms should be fully and unambiguously described by the arguments of the potential, which are its descriptors, and that any possible configuration must be describable in the first place. The accuracy of the entire potential, no matter how many fitting parameters it has, will always be limited by this requirement. In EAMs, for example, this requirement is not fulfilled, which is the method's greatest limitation. Because it only describes distances, the energy of a centered atom in a linear arrangement of, say, 3 atoms will always be the same as in a triangular arrangement, provided the two neighbors keep their distance to the central atom, but not necessarily to each other. This scenario is what's shown here. This is an inherent limitation built into the method. In MTPs, the descriptors are based on radial basis functions, analogous to EIMs, but are combined with angular descriptors called moment tensors. They provide a full basis for local atomic environments and therefore fully satisfy this requirement. In conjunction with the fact that the amount of basis functions used to describe local environments can be arbitrarily varied within the usual constraints of computational complexity, this allows for the construction of interatomic potentials of arbitrary precision for systems that fulfill the assumptions of classical MD runs. Quantum mechanical effects, like the electronic structure of an atom, cannot be captured, though. At this point, we have discussed the properties and quality an MTP can reach if it is properly fitted to a system of interest. However, there exist other formulations of interatomic potentials that may reach similar accuracy through other means, and accuracy is not the only thing that matters in research. The use of any methodology must also be practical, and here MTPs also have their perks. Having a tool that describes a system well and efficiently is great once you actually have a fitted version of it, but getting to this point may be a challenge of its own. The challenge arises in the form of choice of training set, which will determine the outcome of the fit, and therefore be decisive of whether or not the potential will describe the system you want, in the scenario you want, or not. Assume, for example, you fit your potential only to configurations of a bulk simulation box, and then attempt to simulate surfaces with it. Most likely, that won't work. This is an extreme example, and in reality other, perhaps much subtler effects may play a role, some examples of which are shown here: the bulk, surfaces, vacancies, and different crystal structures. In many cases, this means that a researcher has to fit a potential to a set of training data that he assumes is appropriate, and then find a way to validate this fact or publish uncertain results. This process by itself may take months of manual work. With MTPs, the question of whether the trained potential is up to the task of accurately describing a given atomic configuration can be rationalized by a mathematical construct called the DOptimality Criterion. This method relies solely on the current state of the MTP and the geometry used in the configuration in question, and does not require the use of any outside software, in particular, no expensive DFT calculation. The availability of a method to cheaply and automatically determine if the potential is accurate enough to describe a given configuration opens the door to efficient machine learning methodologies that elevate the potential from one that can be well fit to one that can actively learn to describe a system. So how does that work? Explaining the mathematics of the DOptimality criterion would require a video of its own. For now, just assume that we have a function gamma, also known as the extrapolation grade, that depends only on the current active learning state of the potential, which is the current state of the MTP and the configurations in its training set, and the configuration in question, and that outputs a positive real number. The meaning of this number is as follows. If the configuration is well described by the potential, which means it interpolates, gamma is between 0 and 1, the area marked with green in the figure. If gamma is larger than 1, but smaller than a selection threshold, which typically is set to 2, right in the yellow area, the potential extrapolates, but this extrapolation can be assumed to be accurate. If gamma falls between the selection and a breaking threshold of about 5, the red zone, the configuration will still be described reliably, but would improve the quality of the MTP if it was added to the training set. Lastly, if gamma is larger than the breaking threshold, the extrapolation is unreliable. Based on this, a full-flexed active learning on the fly scheme can be built. It involves the following steps. Stage 1. Sampling. Set up an MD run using an MTP. If a configuration with gamma larger than the selection threshold comes up, add that configuration to the set of sampled configurations. If gamma is even larger than the breaking threshold, break the simulation and go to the next stage. If this does not happen during the entire simulation, your potential has become stable enough for the simulation to finish, and you can now get your results. Stage 2. Selection. Select a number of configurations from the sampled configurations, which are as different from each other as possible, and add them to the MTP's training set. Go to Stage 3. Stage 3. Static DFT. Determine the energies, stresses, and forces associated with the new configurations in the training set using a static DFT calculation. Then go to Stage 4. Stage 4. Training. Retrain the MTP on the new configurations. Then go back to the sampling stage. These 4 stages are cycled through until the simulation no longer breaks. When that happens, it is safe to assume that your MTP is stable enough to reliably describe your system and that the properties you measured during the run are accurate as well. The methodology, when properly set up, does not require any human intervention, automating the entire workflow between setup of the system and getting the results, with the possibility of tremendous savings of human labor. Functions for all aspects of potential fitting, active learning, validation, and some pre-processing are implemented in the Mlib software package. It also provides an interface that allows the compilation of the large-scale atomic/molecular massively parallel simulator, better known as LUMPS, with MTPs enabled. This way, VASP is used in the background whenever DFT calculations are required. This usually only happens in the training stage. The Mlib package deals with all questions of configuration selection, training, and testing of the MTP. The fitted MTPs are employed by LUMPS to run MD runs without any further modification of existing code, allowing a seamless integration of MTPs in established workflows. The use cases of MTPs can be directly derived from their properties of being very accurate interatomic potentials that may need 30 to 50 times longer to compute than EAMs, according to our experience. At the Institute of Materials Design at the University of Stuttgart, MTPs chiefly serve as a bridge between simple, analytical models of crystals, such as harmonic or quasi-harmonic approximations, and DFT. In the calculation of thermodynamic properties of systems, one uses thermodynamic integration using Langevin dynamics from set approximations to DFT to efficiently calculate free energy surfaces. These calculations run much quicker if an intermediate system described by a classical interatomic potential is introduced. In the past, EAMs or MEAMs were applied for this purpose. However, the higher accuracy of MTPs allows for a further significant increase in efficiency if they are applied instead. Let's summarize what was said. The class of moment tensor potentials is a highly accurate classical interatomic potential formulation. Its descriptors can capture any atomic configuration accurately, and an arbitrary amount of parameters can be chosen to be used for regression, leaving the choice of balance between accuracy and efficiency entirely in the user's hands. While generally more computationally demanding than EAM potentials, the possible gain in accuracy approaches that of density functional theory, opening the doors for previously inaccessible methodologies. It exists a program that can be used to fit the potentials, the Mlib package, and they can be seamlessly integrated into LUMPS, making the transition as simple as the specification of a different potential in existing codes. For more information and the sources used in this video, you are encouraged to consult the accompanying handout, which can be found in the video description. I thank you for your time and hope that you found this video informative.